Welcome to a lesson on differentiation and curve sketching. This is everything you need to know before we start maximum and minimum questions, which is really the culmination of differentiation. Anyway, the way I'm going to do this, it's going to be like a revision slash, teaching of everything we've done to date. We'll do it by just going through a few questions. And look, a 4-line summary is on the top right, as you can see over here. Y dash tells us the gradient of y. Y double dash tells us concavity of y. Stationary points occur at y dash is 0, and there's potential points of inflection when y double dash equals 0. And we're just going to be applying that. That really is a very, very quick summary of this topic so far. So it says, consider the curve y is equal to x minus 3 all cubed, and it's from a Borkham Hills 2007 trial paper. Find the coordinates of any stationary points and determine their nature. Okay, so stationary points occur when y dash is 0. Right? Stationary points occur when y dash is 0. And you have to write this sentence down. Stationary points occur when y dash equals to 0. You always want to start with that sentence. Always, 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 always. Okay, so let's find y dash. To find y dash is 0, obviously you're going to need to differentiate. And clearly this is a product rule question because you have a function x and then you have another function x minus 3 all cubed. So it's a mix of product rule, and to differentiate the second part, you're going to need the chain rule. Anyway, so let's say u is equal to x, v is equal to x minus 3 all cubed. And so u dash is 1, v dash is 3, x minus 3 all squared, multiplied by the derivative of the inside, which is just 1, so that we're just going to leave it there. And so by the product rule, y dash is equal to u dash v. U dash is 1. V is x minus 3 all cubed, so x minus 3 all cubed plus v dash u. So v dash is 3, v dash x, I'm just going to put x over here, and then x minus 3 all squared. So it's just v dash u 3, x minus 3 all squared times x is just going to be 3x. So I've just skipped a step or so. And I guess we want to know where. Oh, okay. To make our lives a bit simpler, what we will do is we will factorize out x minus 3 squared. So we have x minus 3 squared. Okay, so if you take out x minus 3 squared from here and x minus 3 squared from the right, what will you be left with? So big bracket, you'll have x minus 3 here, and then over here you'll have 3 multiplied by, sorry, I'm going to have to wipe this off. There's obviously going to be a plus there. Okay, plus. So we took out the x minus 3 plus 3x plus 3x. That's x minus 3 all squared. X plus 3x is 4x minus 3. And so where is y dash equal to 0? Because we want to know the stationary points. Stationary points occur when y dash is 0. Where is y dash equal to 0? Well, let's solve it. 0 is equal to x minus 3 squared, 4x minus 3. And by the null factor theorem, we say that x equals to 3 or x equals to 3 over 4. Just either this is 0 or that is 0. And just solving it will tell us this. Okay, so stationary points are at x equals to 3 or x equals to 3 over 4. But what determine their nature? What type of stationary point is there? And so, as I said, I'm going to be teaching / revising. Stationary points. You can have 4 types of stationary points. Okay, so you can have a stationary point like this, as you see in the stationary point. So what is a stationary point? Stationary point is a point on a curve where the gradient is not positive and it's not negative. From a positive gradient to look like this, Negative gradients look like that. And stationary points have a horizontal gradient. That's it. That's what a stationary point is. So if you're taking notes, whatever, you might want to write that down. Stationary points are points where the curve has a horizontal gradient. And you can have four shapes, I guess you could say, 4 ways you can have a stationary point, 4 types of stationary points. So you have like that. You can also have like this. Once again, that's a stationary point. And you can also have something which looks like this. So a curve which looks like that. Like, for example, y is equal to x cubed. Obviously, the x cubed curve looks like that. But as you can see over here, and then over there, or over there, whatever the case, or however you draw the graph, if you have something like that, you can have a stationary point around over there. I haven't drawn it well. So something like this. And as you can see over here, there's a stationary point. Or you can have like that. And once again, you have a stationary point there. So 4 types of stationary points are possible. Now, we are interested in 2 particular types of stationary points, which are known as stationary points. Turning points. Now, turning points look like this or like that. So they were the first 2 that I showed. These are known as turning points. Why are they known as turning points? Okay, so listen carefully. What is a turning point? A turning point is a point on a curve where you have a positive gradient. So the tangent to the curve over here would be positive. Then you have a stationary point here. And then you would have a negative gradient after it. So positive, 0, negative. Or negative tangent, 0 tangent, positive tangent. So these are known as turning points. And so how do we check? Well, it's in the definition, isn't it? I've just taught you that turning points, by definition, are points on a curve where you have positive gradient, then 0 gradient, then negative gradient, or negative, 0, positive. So we can just check that. It's in the definition. It's very definition. So we know there's a stationary point here. We know y dash is 0 here and y dash is 0 there. Now, if you wanted to check, is it a stationary point or not? So we can just check. It's very simple. Like, for example, I know, so we have x and y dash. Okay. I'm not explaining well. Let me just draw the table and I'll explain some more. So, we know when x is 3, y dash is 0. And so it's going to be a horizontal gradient. And this is slope. So I'll write slope here. What about to the left of 3? Remember my definition of turning point? Turning point to the left. So you have a 0 gradient there. But to the left it has to be like this. And to the right it has to be like this. Or it has to be horizontal slope, horizontal gradient. And to the left it has to be negative. And then it has to be positive. So we're just going to check. We're going to check a bit to the left of 3, so let's say 2.9, and a bit to the right of 3. And look, I've made a small mistake in the sense of writing numbers in. 3 over 4 is smaller than 3, so I guess for the sake of, so 3 over 4, which is 0.75, and then over here I will write, let's say, 3. Okay, now in between 3 and 3 over 4, let's write 1. And over here, up to the left of 3/4 is 0. So we're going to check the gradient at 0, at 1. And a bit to the right of 3, let's check 4, say. Okay. And so what am I doing? I know the gradients are 0 at 3/4 and at 3. But what about just to the left of 3/4? And what about just to the right of 3/4? And really, I'm looking for that pattern or this pattern. And if I find that pattern, I can conclude it's a turning point. So let's just go at it. I'm going to sub it into y dash because I'm checking gradient, right? I'm checking gradient. Is the gradient positive or negative? And so I'm going to sub it into y dash. So I'm going to sub 0 in. What is y dash? Y dash was this equation over here. Where is it? Just sub it into x minus 3 all squared 4x minus 3. So 0 equals. And then I will write open bracket ants minus 3 close bracket squared open bracket 4 ants minus 3. And look, if you don't do this, you should learn this technique. In place of x, I'm using the answer key. It makes it really, really quick to substitute values in. For example, I've just subbed in 0, and we've got negative 27. Now, when I want to sub 1 in, I write 1 equals. Now, this is answer now, because that was the last answer I've used. Last answer of the calculator was 1. So I can go upstairs, and when I press equals, it's going to evaluate that expression at the top. But ans is going to be 1. It's going to sub in 1. And it's 4. So it makes it really, really quick. 4. And then if I wanted to sub 4 in, I write 4 equals, upstairs equals, and now it's 13. Makes it very, very easy to substitute. Anyway, so what will my slope look like if my gradient is negative 27? It's going to be grossly negative gradient, right? Something like that. 4 is positive, so it's going to be like this. At 0, it's horizontal. At 13, gradient is going to look like this. And so, which pattern do I have and where? So you need a negative gradient, 0, then, positive gradient, 0, and negative, or negative gradient, 0, gradient, positive gradient. So let's check. And over here, you have negative gradient. Then you have 0 gradient. Then you have positive gradient. And that looks like a turning point, right? It looks something like that. Hopefully you can see that. It's negative gradient. Then at 3/4, it was horizontal gradient. Then at 1, it's positive gradient. And so clearly, that is a turning point by the definition of what a turning point is. So you just have to understand what a turning point is. And using that definition, everything else just follows. And this is not a turning point at 3. Because you have positive gradient, 0, then positive gradient again. That's not our definition. In our definition, we noted that a turning point is a point in the curve where you have positive gradient, then horizontal, or in other words, 0 gradient, then you have negative, or negative 0 positive. And that's positive 0 positive. That's not a turning point. And so from that we conclude. From this, we conclude that this is a turning point. Turning point at 3/4. And look, we're going to sub in. So I'll shorten it because I'm running out of space. Turning point at open bracket 3/4, comma. And you always want to write the complete coordinate where the turning point occurs. So now I need to sub in 0.75. Where do I sub it in? I need the coordinate of the turning point, in other words, in y. So I'm going to sub it into here. I'm not evaluating a gradient, so I would not sub into y dash. That doesn't make sense. I know there's a turning point at 3/4. Remember, I'm trying to graph the function, the original function. I'm trying to graph y. And y dash simply tells me the gradient of that function. Okay, now I want to know the coordinate. Y tells me coordinates. Y dash tells me gradient. Y double dash tells me concavity. I want to know coordinate. And therefore, I'm going to sub it into original function. I'm going to sub in 0.75. And so, answer, open bracket, answer minus 3, close bracket to the cubed. And it's negative 8.4. Can I simplify that? Don't worry. I'm just going to write negative 8.5. Negative 8.5 or so. 8.54, if you will. And so there's a turning point there. And this is a horizontal point of inflection. So horizontal point of inflection at, and it's going to be at 3, comma, I'm just going to sub 3 in. 3 equals, upstairs equals, and it's 0. So 0. And so do I have stationary points? Yes, I have 2 stationary points. Okay. And their nature, what is their nature? Well, there's a turning point at there when x is 3/4, and there's a horizontal point of inflection at 3,0. And that's half of basically this topic so far. Now we move on to points of inflection. Now, once again, if you understand the definition of the inflection, then everything else follows. So just understand what a point of inflection is. A point of inflection is a point on a curve where the concavity changes. That's it. You just have to understand that. Now, y double dash tells us the concavity. So y double dash tells us concavity. Now, if y double dash is more than 0, in other words, if y double dash is positive for a certain value of x, then for that value of x, the curve is going to be concave up. Y double dash more than 0, concave up. So it's going to look something like that. And if y double dash is less than 0, concave down. So sad face. Okay, and if y double dash is equal to 0, no conclusion. It's indeterminate. Like, we have to do more work. Indeterminate. We are not sure. It is inconclusive. Okay, very important. Inconclusive. When y double dash is equal to 0, we're not really sure what's going on there. So, I mean, the concavity, it's not going to be concave up or concave down. Look, we'll get to this in a second. We'll do more work on this in a second. But just the first two, just make sure you understand them. When y double dash is more than 0, concave up. Y double dash is less than 0. If it's negative, concave down. So let me, for example, let me try and give an example. So let's say f double dash 3, right? F double dash 3. What does that mean? At x equals to 3. At x equals to 3, what is y double dash equal to? That's what we're saying. That's what this means. That's what that means, right? And if y double dash is equal to, let's say, 10, right? At x equals to 3, y double dash is 10. That is a positive number. Then at x equal to 3, it's concave up. The curve y is going to be concave up. Okay? Because y double dash at x equal to 3 is positive. Now, if at let's say x equals to, I don't know, 5, say, right? And we found that y double dash was equal to negative 3. In other words, f double dash of negative 3, at 5 was equal to negative 3, right? Then at the point x equal to 5, the curve is concave down. Because y double dash is negative at that point. At x equal to 5, y double dash is equal to negative 3. That means the curve at x is equal to 5 is concave down. When y double dash is negative at a point, the curve is concave down. If y double dash is positive, the curve is concave up. All right, so that's just y double dash in general. Now for the definition of point of inflection. A point of inflection is where concavity changes. So it's very similar in some ways to the turning point. For turning point, we had gradient positive, 0, negative. And now we have y double dash, concavity changes. It means y double dash is positive to the left, and then y double dash is 0, and then y double dash is negative on the other side. So you have concave up, and then you have no concavity, and then you have concave down. More or less, that is how you find a point of inflection. So, two conditions. Y double dash has to equal to 0. Y double dash has to be 0. And to the left, it has to be concave up, and to the right, it has to be concave down. Or the other way around. So a curve is concave up, then it's y double dash 0, now there's no concavity. Then you have to the right of it, it's concave down. Or it's concave down, and then it's no concavity, and then it's concave up. Okay? Concave down, dash, concave up, point of inflection. Or it's concave up, no concavity, concave down, point of inflection. And so that's the definition. Just remember the definition. Where do points of inflection occur? Y double dash equal to 0, and to the left and to the right, you have different concavities. Concave up, concave down, or concave down, then concave up. And that is the definition. As long as you keep that definition in mind, everything else flows. So, let's have a look. It says, find the points of inflection. And so I think we're going to need to double differentiate. There's no way around it. There's going to be another product rule, I guess. So I was hoping to start off with an easy question, but it's just a product rule after product rule. That's okay. You need to get used to it. It's good revision as well. Find a point of inflection. Well, I know y dash was equal to x minus 3 squared, and then you had 4x minus 3, and y double dash, what's that going to equal to? Well, I know let u equal to x minus 3 squared, and let v equal to 4x minus 3 u dash. And look, it's great practice. Pause the video, try it yourself before you watch me do it. If you want, pause at any point, give it a go yourself. That's how you learn. Be an active learner, and you will learn a lot more. Instead of just watching passively, try and get involved. Pause the video, work ahead, and when you get stuck, that's when you should resume the video, and that's when you learn. Right? If you watch passively, you just don't learn maths passively. It just doesn't work. It's a practical thing. It's a skills-based subject. It's not a knowledge-based subject. Okay? It doesn't matter. You think you'll understand it, you won't. It's like karate or swimming. You could watch videos of people swimming all day long, and you wouldn't know how to swim. Maths is exactly the same. You can watch me doing maths all day long, you won't learn a thing. Guaranteed. You have to do it yourself. And look, after the video's over, do these questions again. Go back to the video, do every single one of these questions again and again until you can do it without any help, until you get it right. That's how you learn. Honestly, that is the best way to learn maths. And not by watching. You got to do questions. You're welcome to do the homework questions, or you can do these very questions. It's totally up to you. But that's how you learn. Anyway, so u dash v. So you have 2x minus 3 u dash. V is 4x minus 3. And then v dash is 4. And you have x minus 3 all squared there. Let's just take out x minus 3. So you have 2. We can factorize out the 2 as well, actually. And we can factorize out the 3 as well. And so what do I have left? You have 4x minus 3 over here. And you have plus. We'll have a 2 left over. And you'll also have an x minus 3 left over. And so that's going to equal to 2. X minus 3. 4x plus 2x is 6x. Negative 3. 2 times negative 3 is negative 6. Negative 3 and negative 6 is going to be negative 9. Okay, so that's y double dash. Y double dash. For a point of inflection, y double dash has to equal to 0. And so where will it equal to 0? Well, at x equal to 3. At point of inflection, possible points of inflection at x equal to 3 and x equal to 9 over 6, I think it is. 6 equals 9. 6x minus 9 equals 0. And you have 9 over 6, which is 3 over 2, I believe. 3 over 2. Okay, yeah, so that's our possible points of inflection. Now, remember, by our definition, concavity has to change. And look, I know we've done this already on top. We kind of know x equals 3 already. That's okay. I'm going to do it again because we are trying to learn here. And so, there, 1, 2, 3. And then let's just do this. We have 4x. And now we're going to check concavity changes. So we have concavity here. And what I want to check 1.5. Because x equals 3 over 2. That's a possible point of inflection. And then x equals to 3. And so a number between them is 2. And a number bigger than 3 is 4. Less than that is 0. Anytime you can sub in 0, you should always sub in 0. It makes it really, really easy. Anyway, over here we have no concavity. No concavity there as well. And I'm just going to sub in these numbers here. X equals 0 into y double dash. And so 0 equal to, now I'm going to write 2. Open bracket, answer minus 3, close bracket, open bracket, 6, answer minus 9. That's 54. And so what concavity? Since it's positive here, it's concave up. Now I'm going to sub in 2. Whoops. 2 equals, upstairs equals. And what's concavity is -6, and we have concavity change. Concave up, no concavity, concave down. That's a point of inflection. Point of inflection. And I know that was a horizontal point of inflection. We already knew that from part 1. That's okay. Look, we're just learning it right now. So the point is, this is how you check for point of inflection. What about at 3? Let's see. It's not at 3, sorry, a bit more than 3. So let's check 4. 4 equals upstairs equals, and it is 30 at 4. And that's concave up. And hey, look, you have another point of inflection. That is also point of inflection. Why? Because you had concave down, no concavity, concave up. Concavity changed. So concave down became concave up, point of inflection. And so you have 2 points of inflection. Now that is also a horizontal point of inflection because we know, like, this is a horizontal point of inflection because, at x equal to 3. This, if you look over there, when x equal to 3, remember it was positive gradient, stationary point, positive gradient. So notice it was a stationary point at 3, and it's also changing inflection, point of inflection at x equal to 3, and so it's a horizontal point of inflection. So you can have a normal point of inflection. Normal point of inflection looks like this. See, it's a concave up curve, and now it's concave down. So over here, it's concave down. You can think of it like this, right? It's almost like that. But over here, it's concave up. You can always think of it like that, right? And that's a point of inflection. Notice that in the graph that I just drew, so look over here, it's concave up. This is not horizontal gradient at any point. It's diagonal. When it changes at the point of inflection, at the point where the concavity changes, it was not horizontal. The tangent looks something like this, more or less. Very rough drawing. Probably looks something like that, actually. Something like that. But yeah, it's not horizontal. And that's a regular point of inflection. Like 90% of point of inflections are regular points of inflection. Sometimes you have horizontal points of inflection, which is where you have a point of inflection at the same point. You also have a stationary point. So, which looks something like this. Notice horizontal. It's completely horizontal. Is concavity changing? Yes. Is it a stationary point? Yes. Both at the same point. That is known as a horizontal point of inflection or a stationary point of inflection. Just be aware of them because it says sketch the curve showing clearly all features. So we need to kind of know what it looks like. So let's see. What do we know? All right. So highest power is to the 4, x to the 4. It's going to be positive because when you expand this out, x minus 3 all cubed, it's going to be x cubed. The highest power is going to be x cubed multiplied by x out the front, x to the 4. It's going to be positive x to the 4. Now, because it's positive x to the 4, I know it's going to start somewhere there and there. Because for really, really large and really, really small values of x, x to the 4 is going to dominate, so to speak, and nothing else will matter. X to the 4 is going to be hugely positive or hugely negative. It's going to be like that. And what else do I know? Let's see. I know that the y-intercept will probably be negative. Well, I'm not sure, actually. That's okay. Let's just stick to what we know for sure. There's a turning point at 0.75 and negative 8.5. So let's just jot that down. Where is it again? 3/4. So let's say this is 0.75. And at negative 9, there is a turning point. So it's going to look something like this. There's a turning point there. Great. Moving on. What else do I know? I know there's a horizontal point of inflection at 3, 0. Okay, so let me just mark this in. This is 0.75, right? That's 0.75. This is going to be 1.5, right? And let's say 3 is going to be somewhere like there. Now, how did I choose those numbers? This is because if you look over here, I've got something special happening at 0.75, at 3, and at 1.5, which is why I've labeled those. Now look, just so that we have more information and so we know what's going on in a bit more detail. I know the horizontal point of inflection is at 3, 0. Okay, and we don't know the y coordinate of 1.5. So let's find that out, just so we have more information, for the sake of completeness. 1.5. So I'm going to type in 1.5 equals 2. And then you have answer, open bracket, answer minus 3, close bracket, all cubed. -5. So point of inflection, that's at 1.5, comma, -5, roughly speaking. Okay, so notice how to the left of 1.5 it's concave up, but to the right of 1.5 it's concave down, and so it's going to change at -5. Remember that was -9. Was it -8.5? Was it? I think, yeah, -8.5. Right, -8.5 was the turning point, and at -5, it's going to be, so it's going to be going up, and then it's going to change. So it's going to be like concave down now. So over here, point of inflection. It just says showing clearly all features. So point of inflection over there, turning point there. Okay, it was what's gonna call it? So it's a turning point here. Look, I'm just it's really bugging me. What is this curve? Where will the be? The y-intercept. The y-intercept occur when x is 0, and so when x is 0, it's going to be 0. The whole thing's going to be 0, and so the y-intercept is at 0. Great. It was bugging me. I was thinking it's -27, but I forgot the x at the front. So y-intercepts occur when x is 0. If x is 0, that x becomes 0. This is 0. 0 times anything is 0, and so y-intercept is at the origin, right? And so that's what my curve is going to look like over there. Now to the right, notice it was concave up. Point of inflection changes concavity. It's now concave down, and there's a horizontal point of inflection at x equal to 3. And so it's turning, and now notice at a stationary point, now it's going to become concave up again because there is a point of inflection. That's why that's x. We can, hopefully that doesn't take too long. Come on, where are you? So yeah, let's just plot this for the sake of curiosity. Explicit, and we are doing x multiplied by open bracket x minus 3 close bracket power of 3. Yes, and so as you can see, we got it right. I mean, more or less, that's exactly what happens. And look, if I zoomed out, you zoom out, and yeah, look, we got the curve right. We got all the main features right. We could stretch it horizontally. I can't be bothered. The point is, we got it right. That's a lot of working out. Heaps, tons of working out. That's this chapter. This is why this is kind of like the culmination of differentiation. This topic is what NESA uses to differentiate between band 5 and band 6. It comes up every HSC without fail. Every single HSC. It's one of those topics definitely examined. Definitely. And look, I worked through this question very slowly. Very, very slowly, explaining everything. That's why it took me 33 minutes or so. When you do it, it should not take you more than, let's say, 5 minutes or so. It really shouldn't. Let's have a look at another one. And that was a particularly tough one. If only because differentiating it was a bit of a pain. With product rule, chain rule, that stuff. Let's look at this question. You have 4 over 9x cubed negative x to the 4 over, or 1 over 9x to the 4. Find coordinates of the points where the curve crosses the axes. Where does the curve cross the axes? Well, for starters, where is the x-intercept? X-intercepts occur when y-intercepts occur when x is 0. And so when x is 0, y is going to be 0. And so we know straight away that the y-intercept is over here. And where the curve crosses the x-axis. And so x-intercepts, y will be 0. So when y is 0, you have... so let's factorize out the x cubed. And then you have 4 over 9 minus x over 9. And those are going to be my x-intercepts. x 0, we already know that. And over here, using null factor theorem, 4 over 9 minus... And we could have factorized that to 1 over 9 actually. Let's do it now, 1 over 9. And so we'll have 4 minus x equal to 4. And so the coordinates of the x-intercepts are going to be there and at 4 over 9. So let's mark that over there, 4 over 9. Sorry, just 4. Why did I say 4 over 9? 4. 4 minus x equal to 4 is a x-intercept. Final stationary points. Look, this is getting longer than I intended. I have to go as well. This took really long. Look, just watch the video, do this question again and again until you understand it, and I'll be happy to do more videos later on. So best of luck. And yeah, let me know if you need help on Slack.